Good afternoon. My name is Dale Brosius. I'm the Chief Commercialization Officer for IACME, and this is Innovation Insights for March 2025. So we're already almost a quarter of the way through the year, and it has flown by. And by the way, happy St. Patrick's Day to those of you that observe it. And want to just open up with a couple of quick slides about IACME. This is a slide I use every month, but organized around convene, connect, and catalyze, bringing people together, connecting them to each other, and making great things happen through a number of avenues that you see surrounding this, including funding, meetings, consulting, and training education. If you're not an IACME member, you just go to iacme.org/members, and you will be able to, give us the information we need to be able to send you what you need to become a member. Just a reminder for those that are members and prospective members, you can still join. Our members meeting is June 24th through 26th in Dayton, Ohio. This is our 10th anniversary of IACME. We'll be celebrating in grand style. So hopefully you can go there. We just came back 2 weeks ago from JEC World, again, celebrating the decade of innovation with 45,000 of our closest friends and 1,300 other exhibitors we were on the U.S. Pavilion there. So it was a great show, great event, and IACME was well represented. We will be at SAMPE in May, so plan to see us there. At SAMPE, a great program going on at SAMPE this year in Indianapolis. It's a great venue, great town. I happen to live in Indianapolis, so I want you to come to this town and experience it the way that the locals do. It also is the week just before the Indy 500, so for race fans, you can stay over and see the race. Just a reminder, Innovation Insights is archived on our website, so we've 33 episodes prior to this one since early in the pandemic, featuring over 100 members and partners. Again, all the episodes are recorded and stored on our website and available through our YouTube channel. So if you've got a colleague that you think needs to see something that you'll see today, make sure you let them know. A couple more episodes coming up before our members meeting, Monday, April 21st and Monday, May 12th. We still have a few slots available for those months, and we'll fill those fairly quickly, but those will be on a Monday at noon each of those months. So today, and I'll get ready to hand it off, we have presentations from three great entities, from AlphaSTAR, from Dassault Systèmes, and from Oak Ridge National Laboratory. But just before I do hand off the presentation, I will note that please put any questions you've got in either the chat or in the Q&A, and we will get to as many of those within the allotted time as we can. So with that, I will just turn it over to our first speaker, who is Dr. Harsh Baid, Chief Scientist at AlphaSTAR, and his colleagues. Take us forward. Harsh?
Yes. Hi. Thanks, Dale.
Share your presentation. We will move on.
Can you guys see the screen?
Not yet.
Let me try to share.
Just put it in slideshow mode and we will be good to go.
Perfect. Okay, thank you, Dale, for the introduction. Hi. This presentation today is going to be about additive manufacturing build simulation for polymer material extrusion with advanced materials. I'm going to start with the agenda slide here. We're going to introduce our company with our product portfolios, talk about additive manufacturing build simulation, value of simulation, and ICME workflow. And then we're going to go through some of the case studies in both from the FDM side and for the large format additive manufacturing side. Myself, Harsh Baid, I'm the Chief Scientist here at AlphaSTAR. I have other two co-presenters today with me. We have Dr. Sarat Kundurthi, our research scientist, and our additive engineer, Mr. Arjun Marrey, with me. So about AlphaSTAR, we are a developer of physics-based simulation engineering software for advanced materials and structures. We have a track record of 35 years providing solutions in the area of composite modeling, virtual manufacturing, and virtual testings. We have a global customer base in the area of aerospace, defense, automotive, energy, and research institute. And we have published over 400 publications throughout the years and authored a few books as well. We have deep-rooted affiliation with the US DoDs and research institute globally. And we have been involved in enormous market opportunities throughout the years. On the right-hand side, you also see that we have received multiple awards throughout the years from US Senate, NASA Software of the Year, and also we have got multiple times R&D 100 awards, both in the additive side and also the non-additive side. This is our advanced product portfolio here, simulation-based engineering solution for advanced material manufacturing processes. We have three major software tool sets here, starting from the left-hand side, which is the material modeling, which is called MCQ, material characterization qualification, for continuous composite, discontinuous composite, ceramics, metals, and nanoparticles-based composite as well. The purpose is to characterize and qualify material properties. We want to generate the database with limited testing, and also we call it the qualified material system database. So this is one of our core capability of doing the material modeling using micromechanics approach, followed by additive manufacturing process and also virtual testings. From virtual testing side, it's a Genova multi-scale progressive failure analysis. That's what the software name is. The purpose is to do, again, multi-scale ICME based structural simulation toolset, so that we can predict the physical behavior of the manufactured part considering effect of defects under different loading conditions, whether it's static, fatigue, under environmental conditions, impact, and any dynamic analysis, so that we can accelerate the time to qualify products. And thirdly, we have the Genova 3DP simulation, or additive manufacturing modeling and simulation toolsets, which creates a predictive, digital twin aspect of what's being printed and identify the mechanical behavior of the as-built AM part. So that's the purpose of the Genova 3DP simulation. My other co-presenter here, Sarat and Arjun, they're going to be presenting the rest of the slides. We should go more in depth into our additive manufacturing process, AM process, and simulation. Sarat, I would like to hand it over to you from next slide, please.
Thank you, Dr. Harsh. So this slide shows the value proposition of simulation in the context of additive manufacturing. We know that additive manufacturing is inherently an iterative process. So if you were to print blind without any simulation, you would end up with a bad part inevitably, which would then require multiple iterations to fix either your warpage, or maybe you're experiencing build failures, or maybe the part is not able to withstand the loads as intended. So instead, what we are proposing is, instead of printing blind, you first simulate, identify what's going on with the part, compensate for your warpage. If you see any potential problems, potential build defects, or so on, take appropriate action before printing it, so that once you hit print, you have a much better chance of ending up with that first time right print, and this eliminates the need for trial and error. So this is like a very high level overview of why we need simulation in additive manufacturing. This slide talks about the workflow that we use in order to achieve this. So on the left, we see our design and build prep. So this would be your typical design your geometry in CAD, set up your build tray, slice it, and then normally at this point you would send it to the printer. But instead, on the right is our Genova 3DP ICME workflow, where we start all the way from material modeling, and we generate anisotropic properties for material qualification. So if you have a fiber filled system, for example, you can utilize our material modeling toolset to generate all the required anisotropic properties, and also generate temperature dependent properties, and then feed that into the rest of the simulation. And these properties are also dehomogenized, so that where you can also combine all three products that Dr. Harsh mentioned, our material modeling, our progressive failure, and our additive manufacturing tool, for a true ICME workflow. That means that you can predict the defects in the part, how they initiate and how they propagate, not just during the loading, but also is there any damage accumulated during the build process. And to simulate the build process itself, we use a two-stage approach. We start with a transient thermal simulation, which is toolpath driven. It's not a layer by layer. It is a time-based solution which follows the toolpath sub-layer. So it results in a much higher resolution and a much more accurate time temperature history. It considers the GCode and if there are any support structures, rafts, stabilizers, all those kinds of things, it is automatically picked up by our GCode translators. It picks up any controller effects, variable print parameters, and also your environmental conditions, your radiation convection, and so on. Once you predict the thermal temperature that is happening at every stage of the print, we take that information and feed it into a mechanical build simulation, which is an FEM model for predicting the behavior of the part as it is being built. So we can then predict the deformations and residual stresses and damages in the part as it is being built, and then map that information onto a finite element mesh for applying in-service loading. So we can then perform your service analysis on a realistic part that incorporates all the build defects. To go into more detail on material modeling for chopped fiber filled systems, uses a nano micromechanics based approach where we generate equivalent laminate properties for the given orientation at every element. And this then is dehomogenized all the way down to the nano micro scale. So we can then take at every iteration of an FEA model, we can then predict the stresses and at the constituent level. So then we can predict all damage at the micro level. So we redistribute the load between fiber matrix and also the interface. So we consider all these effects, which then feed into our macro scale prediction. And then in addition, we can also use our Cure Kinetics module to predict temperature dependent modulus and a multi-factor technique to predict temperature dependent strength in multiple directions to capture the entire anisotropic behavior. Okay, now specific to the 3D printing module, these are 3 examples that demonstrate how our solution can scale. So on the left, we have a more, you can say, an academic study where we're looking at a relatively simple geometry, but with lots of validation data to predict how this wall is deforming as it is being built. And this was done in collaboration with Oak Ridge National Lab. On the middle, we have the Genoa 3DP software applied to an FDM example. And this is a very complex shape. And this was on a Stratasys F900 printer where we had to consider the effects of build plate interactions, your vacuum build plate, your environmental chamber, your intricate support structures, and so on. On the right-hand side, we have the same tool being applied to a very large part, which is a modular home. This is a gigantic part, 9 feet tall. And we're incorporating a different sort of complexity, such as you can see the rotating table, which is being pulled off the bearings because it deforms so much, and also controller related aspects. So this shows how our software can scale and is validated at different levels of complexity. Now I'll hand it over to Arjun, who will talk more in detail about each of those cases.
Thank you, Sarat, for setting everything up perfectly. So in the previous slide, Sarat showed 3 different example case studies, 2 on large format additive manufacturing, 1 on FDM. So in the next 3 slides, we'll be looking at the same examples, but more from the application perspective. So this slide is on the vertical wall validation. This is a large format structure. It's a 2-bit structure, more research oriented work where when these 2 bits are printed, the bottom thin aluminum sheet is warping a lot. So what's the challenge here is, can you simulate this from 2 sides? One is have a temperature validation in the when they printed it realistically, they captured all the temperature data. So validate temperature first, and then go to the second stage of taking that temperature and mapping it onto a mechanical analysis file so that we can predict the warpage that's happening. So that is the agenda for this specific example case study. So again, for any analysis, we start from the material side, because if we don't have the right material properties, no matter how perfect we design the simulation, it'll never give us the right response. So for that, we start from going from left to right. We have the material modeling. As Sarat mentioned earlier, we use two different analysis. The one is pure kinetics to come up with the temperature dependent modulus. For anisotropic, here this is a carbon fill system, ABS with 20% carbon fiber in it. So capturing all direction E11, 2, 2, 3, 3. Once we have the temperature dependent modulus completed, we go to the next step where we use multi-factor technique to predict all the strength properties, which is shown on the left-hand side bottom. Once we have the material modeling complete, the end product of the material modeling, if you look at the left side pillar, is we get a material card, user material card, which has all the temperature dependent properties along with user defined damage and failure criteria. The user will specify this is the damage criteria I want to capture in my simulation. Once we have that, we go to thermal analysis, where bringing in the G-code that's being used to print, we simulate it, create like a realistic build plate. In here, we have a build plate. On top of that, there is a thin aluminum sheet which is bolted down, on top of which it's printed. So we bring all that detail into the thermal analysis, because thermal is the backbone. So we have to get the right thermal response so that we can trust that thermal will predict the right mechanical response. So on the middle pillar, we can see that we simulated the temperature, and on the bottom, that's the validation. The dark lines are the temperature that's captured from the simulation, whereas the dotted lines are predicted from the thermal analysis. Once we have thermal completed, validation complete, we take the thermal to a mechanical where we solve for stresses, displacement, warpage, and also damages. So there are two things here. The picture, if you look at the right side pillar, middle picture, that animation is showing you how the aluminum plate is lifting off as you keep depositing each layer and go through the entire build process. And the bottom picture shows you the validation of, as you keep going through time, how the deflection is accumulating throughout the entire simulation, and then comparing that with the experimental result. Here, the key thing is, it's not just about temperature and displacement, but also if there are any damages that are initiating during the build process, and how are they propagating. That is something we capture in our analysis as well. And if we go to the next slide, this is an example on the FDM Stratasys F900 machine. So the material is Ultim 9085. Here, in the words of Stratasys, they call this geometry the torture test geometry, because this is warping so much. So what are the colors we are looking at over in this slide? Is the blue means it's undersized, red means it's oversized. So if you look at the left side picture before, which means it's a blind print. The traditional way of doing this, as Sarat explained, is it's print and see and adjust. So you print, you see, and then you adjust, and then print again iteratively, so that when you, at the end of the day, you want to come up with a part that qualifies for your requirements, not performance. At least in this case, it's a net shape requirement. So if we go with the blind route, you can see the out of tolerance values, 28.67 points are out of tolerance, which means the tolerance we are comparing at here is 0.011 inches, which is about 280 microns or 0.28 millimeters. So at that given tolerance level, a lot of points are out of tolerance, and the points that are out of tolerance are way out of tolerance. It's not close to 0.011, it's way out of tolerance. Now, what we showed earlier, which is instead of going blind print and iterate physically printing these geometries, how about we simulate it? We bring the G-code in. In this case, it's F900 machine. We bring the G-code in from the slicer. We bring it in with all the customizations for that specific machine. We simulate it so that at the end of the simulation, we predict what's going to happen if you print this specific geometry in that specific machine with the specific build characteristics that are intrinsic with that machine. So once we predict that geometry, deformed geometry, we create a compensated geometry out of that deformed, out of our predictions, and then tell the system to, okay, now go ahead and print this compensated geometry so that you'll have a better chance of getting a green part, first time right part. So that is what we did on the right hand side. We simulated it, we predicted the deformations, we created compensated geometry, send that compensated geometry back to the slicer and ask the machine to print. Once we printed it, if you look at the number of points out of tolerance, so previously the blind print, it's 28.67% out of tolerance. And now just by running one virtual simulation loop, we are able to bring it down to 10.66% out of tolerance, which means, and on the score, if we look at the score, the scoring scheme is Stratasys specific scoring scheme. So here we went from 56 to 71, which made a poor print or a bad print to a good print above 70. So we are able to reduce the excessive distortions and create a green part, which meets the net shape requirements. And the final slide here is on the large format additive again. So here, this geometry, just a bit of background on this geometry weighs 3,500 pounds. And the material cost, if we go with the traditional route of print, see, and adjust, which means the material cost itself is roughly about $15,000 to $20,000. So which means if we go the traditional route, you print, see, adjust, correct again, print. So you're accumulating 15, 20,000 at a time, which means if you come to a good part at 5 iterations or 10 iterations, by that time you already spent 100,000 or 200,000. That was what's happening. And that's when the company came to us and asked us, can you simulate this? Can you simulate and show the deformations or warpage that are happening? And is there a way to fix that? That is where we started. So here, for large format structures like this, the GCode and then the controller changes, both are important, because the GCode might say that the print only takes 31 hours. In this case, it said 31 hours. But whereas the controller on the fly, the adjustments, because it cannot hit the same speed at the corners, it has to decelerate and accelerate. And depending on other parameters as well, in reality, the controller is making few changes. So those need to be considered as well, which means we need to create a hybrid GCode where you take the original GCode and you take what controller is doing, bring it together, and then feed that to simulation, where in this case, it's 31 hours and then the actual print is 40 hours. So there is like 9-hour difference. So considering all that, again, a lot of customization for the specific machine. Once we create a when we say customizations, for this system, there is this build plate that's rotating, which is clamped down, release the clamps. So there is a lot of details that need to be captured. So once we customize the solution, which means it's good to go. Now, in the same machine, same setup, if you plan to print a different geometry, we did all the hard work creating this customized solution, which means now you can go ahead and use that for other geometries on the same machine. That's what we did here. We simulated it going from left to right again, print, the video shows the print. The bottom is the simulation, bringing in the hybrid GCode from the GCode and on the controller. To validate our predictions, we scanned the geometry just to showcase that, yes, the simulation is able to pick up all the details. So the scan deformations are we actually printed this geometry, scanned it, and the simulation predictions where you can see that, again, here, because it's large format, these blues and reds are gigantic numbers. Blue is bowing in a lot, red is bowing out a lot. So in this case, simulation is able to pick all those details as close as possible to the reality. With that, we moved on to the next step of, okay, now the simulation is able to predict everything perfectly. How about compensating it and see if compensation is able to solve a lot of these issues? That's the validation on the rightmost pillar, where the blind print, which is no printing, no simulation, just get the GCode printed, where you can see one side of the wall here, which is extremely wavy. And here, because the structure is gigantic, when we say wavy, here we are talking about 10, 20 millimeters in and out. So if you can visually see it when you look at the structure. So based on simulation, we created the composite geometry, printed it again. And now with that, we can see the side wall, it's 80% to 90% improvement. That waviness is completely gone. Even though there is like 1, 2 or 3 millimeter waviness given the structure, it's almost completely flat. And that's the improvement on the side walls. Whereas on the big walls, where these are the roof and the floor sections, where the original print, the blind print, showed that red spot, which is extremely bowing out where the cross section changes, and also the bottom bowing in, those are drastically reduced. So with, again, one round of iteration, we're able to show that, yes, instead of spending 15 to 20,000, how about you simulate it, which once we customize everything, it's very easy to simulate. You simulate, you compensate, and then you're able to reduce most of these warpage and deformation issues that you are getting when printing these structures. And one good thing is, obviously, this is our first round of iteration, but how about we create a virtual loop, and instead of doing it physically, create a virtual loop so that you can not only just improve the quality, but also make informed decisions when you're designing these structures, keeping in mind the deformations and also the stress aspect as well. That is the overall value of implementing this ICME-based additive manufacturing solution. That is it for the presentation. With that,
Great.
we'll open the floor for questions.
Yeah, we've kind of gone over time for the allotted time. There is a question in the Q&A. I'd appreciate if you go in and answer that. I'm going to put one in there as well that I have, but if you can go in the Q&A panel and answer that, that will be useful. And I want to say thank you to the AlphaSTAR team. And if anybody else has any questions, they can put them in the chat or the Q&A. And then if you guys hang on and answer those while the other presenters are presenting, that would be appreciated. So thank you again.
Okay.
Okay, stop sharing and then we'll move on to our second presenter. Our second presenter is Dr. Pierre-Yves Méchin. He's a composite R&D director for Dassault Systems based in Paris. And Pierre-Yves, if you want to start up your presentation and we'll move it along.
Just starting now. Can you see the presentation?
Perfect. Yes.
Yeah, I
we're
think
good.
it's working. Okay, thanks for the introduction. Hello everyone. That's really a pleasure having a chance for this this presentation today. So I say my name is Pierre-Yves Méchin. I'm part of Dassault Systems, probably well-known company for 3D modeling and simulation tools, with some recent development around the 3D Experience platform. And my work is to be in charge of composite material topics and composite materials and materials. So offering the applications for composite design, working closely with the simulation and the manufacturing. But at the same time, those materials are actually created and at the same time than their microstructures. So we need to have a clear understanding of what's happening at the different scale of the materials. And well, so this presentation is an opportunity to get in the details of what we do at Dassault Systems around this. As a brief introduction, our company is large company created in 1981. And we are more than 24,000 people working over the different countries. We really try to work for manufacturing products, but not only. There are a lot of other topics about infrastructures and life science. And well, this is long-term company as it has been created more than 40 years ago, and really having a long-term vision about the plan we want to cover in the coming years. We have a network with a lot of resellers and partners to make successful our 3D Experience platform. And we have a lot of customers around the world for the company. So just showing a few words to get back to the history of the company is that it was starting with the 3D design, and where really the purpose was to move from 2D to 3Ds, then shifting to having a clear digital mockup of all of this, extending to the management of the life cycle with the product life cycle management. And then in 2012 came the 3D Experience platform, which is a place where we have all the products that are offering the ability to create some virtual twins for experience of viewing, and more widely recently saying that we need to provide a more sustainable world, and we expect with the 3D Experience platform that we can contribute to this. More practically, what does mean the 3D Experience platform is really a bench of millions of applications that can be working together to cover a workflow, multiple workflow. And this is really an efficient place for composites to work on, where we have multiple applications covering some conceptual design to detailed design to manufacturing preparation, covering specifically all the composite manufacturing processes, composite forming, breading. We are about to release a new methodology for filament wanding. Well, so we try to cover all the specificities of the composite process. And where I would like to focus today is on this one, which is more related to the material. It's a material virtual exploration world. What the purpose is really, can we have some understanding of how the material performance will be driven by manufacturing aspects. Briefly, we'd like to introduce some challenges, focus on what we've been doing with this material virtual exploration application, and give some finesse. I think it has to be a quick presentation, so I try to be sharp and efficient. Basically, what we try to cover with the app is the fact that the composite materials really is really driven by the multi-scale. It starts at the atomistic scale, where we have to do some well, I will recover the name, but we do atomistic computation, where really is to understand the dynamic molecular effect and how the polymer chain will be arranged to have mechanical response of the resin on the fiber on at some point interface. But those methods have to be involved in a larger scale for multi-scale analysis, giving some properties for, well, let's say material composite plies, and those composite plies are involved in larger substructures which require to define coupons, and the coupons result are driving the way we do the design of a product development, which can be pretty large, showing an aircraft, but could be a smaller one. And the fact is that we have to do virtual twin of all of that, but at the same time, we have to get some insight and input from the real world. And this is really place where we expect to have exchange of information and images and data between the virtual and the real world. And the purpose today is to focus on that part where we really want to model complex complex microstructures of the material and offering these capabilities to engineers who are looking for properties without necessarily the knowledge to set up and use such materials, such tools. Basically, for composite, as I said, we have some fiber, we have some resin, but we have a process, and that process is leading to some specific, let's say, defects. And the challenge is to understand if those defects are critical or not for the purpose we are exploring. Just for an example, if we looked at composite material microstructures, we can see that there are some plies being assembled together with some interfaces between the plies, and we see some area where the fibers are well aligned together, and some area where clearly there are rich resin area, and we expect to understand what will be the variability of that microstructures, because this is a place we would have some delamination being initiated, and we have to understand what's happening behind this. Well, so what we try to model in the platform is basically with the 3Xperience platform to model all the scales. So here we have a wind blade, and the idea is to show that we can zoom in the different structure definition level. We have a sandwich structures, sorry, where we have clearly plies and some honeycombs, and we can really model the patterns for the different aspects. So let's start with the honeycomb. The honeycomb used to be an hexagonal cell where we have to model this with different combination. We have some resin around, which is usually related to the fact that the plies above, we have extra resin coming to the honeycomb. So we have to model what is the effect of the resin on the effective stiffness of the honeycomb. We can model woven pattern, and here we're just showing the fact that we have a model of the microstructures, but we of course have the meshing of this, so we can run any structural simulation on that microstructures. Getting at the lower scale, we have a random fiber arrangement. Fiber usually have a different diameter, could have a different shape, and we have to understand what is the effect of this variability. Getting in a resin, we used to have some void in the resin, which could be or could not be critical, but the idea is to be able to model this variability of the void shape, aspect ratio, and orientation that we can consider. So this is really what gives us the 3Xperience platform, is the ability to model with a given knowledge all the microstructures at the different level, from the product level to the detail scale. Getting the details, we have some constituents. So we have a resin. Usually the resin is pretty straightforward to measure. We can do tensile tests on given resin system. Not necessarily easy for thermoset resin, which are the property of composite material suppliers, but we can try having some physical tests from this. Well, I mean, physically, this is easy to test. But on the other side, the fiber is not easy to retrieve, so we have to make assumption or identification for the fiber properties. There is an extensive literature about that, but the idea at some point is, as the fiber is isotropic, anisotropic, how we can retrieve proper properties that we have to use for the multi-scale simulation. So there is a challenge, and we have been spending time to create a database for both resin and fibers. Well, actually the resin we got access to, but the fibers are typicals and classify according to their stiffness, and we can model this. Now we need a model to change scale, and the change of scale is given by representative volume element. So we are really able to model very complex RVEs, retrieving the variability of the microstructures. And on top of that, we have to apply some boundary condition and load, which usually described by periodical boundary condition. So all those steps are really the expertise of material engineers. And at some point, what we want to extract from this is the mechanical properties of a given material. And what we want is to provide to engineers integrated tools to get those properties without the need to have a clear understanding of fiber effect and how to model the RVE. So the 3D Experience Material Virtual Exploration app is an app part of the 3D Experience platform, where the user can interactively and quickly set up microstructures, part of a study. So really the user select given list of predefined microstructures for any type of microstructures, any materials. So in that case, we started on lattice structures. So we have the visual of the lattice structures, which is driven by some parameters, the beam radius, the cell size, and the number of patterns we can have. And from this, we can apply the typical loads and boundaries we want to compute, and we run the FE solver, which is Abacus solver, to predict the properties. So we get homogenized properties of this, elastic and nonlinear properties for the different loading type that we have. And from this, we can have a material that is possible to use at larger scale. To get further, just other example, we can actually do that for composite, which is a place it's pretty useful to have RVE models. We can have a hexagonal regular RVE, which is a very simple one. But in that case, we have been able to train an AI model from which we predict the properties. So we have AI model we've used an AI model to train some RVE models to reduce the time of prediction, because an FE solver is usually something around 1 to 3 minutes, depends on the accuracy of the mesh. But for the inference of the AI model, it's just immediate prediction. And the value of this is that we can then compute a large amount of different model configuration, where we can have an understanding of the variability of the properties. And this is really where it comes interesting to use the AI for such multi-scale model, is really the ability to not chase for a single property, but really chase for an understanding of mean values and standard deviation for elasticity, which is not varying much, but for plastic response or failure response, I think it's getting more efficient to have this. So, well, we can do some FEA computation. It was just longer to compute this, and we have all those to this part of the project. We're able to deal with different microstructures again, and this is quite an interactive new app where we model the complexity of the microstructures. For the AI model, actually, we've been using some TMN models, which is quite efficient for the material multiscale prediction, where we make a balance between test and training. So we do training for different volume fraction, and we do some tests to validate how it works. So it responds pretty well to the variation of the volume fraction, of course. It's exhibiting some slight difference for the effect of the arrangement of the fiber, where we are really looking for proper response, as the fiber arrangement is quite the reason we would have some variability. So there is still some work ongoing that will be done by the release of this new application next November. Well, so I've been chasing a lot for composite material, long fiber composite material, but we worked a lot past year on the short fiber RVE models with really the challenge to have high aspect ratio and high volume fraction of RVEs. So what we have here is how we can actually generate some microstructures which combine high volume fraction and high aspect ratio. This is work under the way at the moment. And interestingly, it shows that there was some physical tests from 1996, which were produced composites, and we can see that our model is able to predict to recreate the microstructures of the past model created for the experiments. So this is work under the web. Basically, this is a view of the fiber randomly arranged with a control of the tensor orientation for the fibers and the resin system around, which is well controlled for the mesh point of view. So just to show them that we have an accurate RV, which is efficient compared to, some solution I've been actually developed in the past. Also the same for woven. So with the woven pattern, we can have multiple patterns of toe definition together. We have some meshing around, and this is also a topic where we are working a lot. We are trying also to work closely with physical tests to really validate that our RVs are relevant for the future. Back to long fibers, we have been working extensively of random RV model with different strategy to build the RV models. Basically a smooth distribution where really we control the position of the fiber smoothly distributed on microstructures. We have some cluster model where really we exhibit some rich resin area. It has been extensively published with some different strategy to create the rich resin area. Not necessarily easy methodology. So I think this one is really useful because at the end we have a unique spread random RVE, which is able to create all the combination of the fiber arrangement that we can have in a real life. And our idea is this, we were able to retrieve the variability of the picture at the bottom right, where we see that they have some rich resin area and control of the distance between first neighbors. And interestingly, is really something we can do with the material virtual exploration and retrieve the variability of the composite, in that case, composite strengths for such a complex microstructures. And we see that the random fiber arrangement is pretty impacting transverse properties and shear properties. Well, so I've been talking a lot about microstructures, AV, and components. We have just to extend where we go now. Is the fact that we have an effect of the curing process. So we've been doing some testing where we have different cure. The different cure lead to different degrees of curing for the resin system. And we are able to introduce the resin properties into multi-scale models to see if we can understand the effect of the curing on the defect that we get at the end. So we have been doing some prediction of, in that case, again, the composite strengths and compare some experiments to prediction with pretty good accuracy. So that's getting in the right way. And behind this, there is really the need for more complex RV to be defined. Focusing again on the compression is that we need to create from the random RV model different fiber arrangement along the length of the RV with the fiber waviness. So we can recreate fiber waviness with a given distribution of this waviness thanks to physical analysis of images. And we really recreate efficient model from which we can predict the snapback, typically snapback of compressive strengths that we have. I think I'm running shortly out of time, getting faster to the conclusion. We have with the platform some ability to combine the modeling and the simulation and being able to do some efficient prediction of what will be the real world from the virtual world. We have material science app, which is accessible to engineers for the product development, meaning you're developing a product, you need to understand what is the variability of the material, but not how you get it. And there is a new app being released on the platform next November. And I think there's some testing possible for people that would be interested around. Just get in touch with us. Next step is continue extending to a large amount of microstructures, different microstructures, not focusing on composites only. And we try to release some in some results on papers where we demonstrate that our microstructures models and what we do on the platform is actually consistent with the real world. So there are a few papers around here explaining more in the details what I've been showing shortly in 15 minutes. And that's it. Just thanks the whole team in Kutia that have been working on the app. Same for Similia and corporate research that all contribute to this. And we work closely with the University of South Brittany to have the physical test result that are compared to our virtual prediction. Being quick, but I think it's done. And thanks for the time for this presentation.
Thanks, Barry. Yeah, there's a lot to digest there. It's a lot of information. And,
okay. I hope I was not too long.
Well, you had to go. You went quick, and I appreciate that. So it's probably one of these things I'm going to go back and have to watch again to fully gather it all. One quick question is, this whole idea of virtual allowables has been around for a long time, and it's been tough to build confidence in people. Want to make sure that they make and break to validate things. Is AI going to help us get over that hump?
Oh, yeah, I would say yes. I think, well, multi-scale model is really something that was existing for a long. I think Steve Tsai introduced that in composite material theory mostly 50 years ago. The question was that we didn't have any computation sufficiently efficient for such prediction. And same with the FEA prediction. It was too long to expect from multi-scale model to have a clear understanding of the variability of failures and material delamination and so on. And I think AI was really an area where it can completely change the way we could embody multi-scale design through the product design. Clearly.
Yeah, I'm seeing it coming. Obviously, the power that we have now is helping us along that way. So appreciate your presentation, and again, being archived, we'll be able to go back and watch it again and recommend that others do as well. So again, we also appreciate Dassault's support of IACME throughout the last decade, and look forward to our continued relationship. So
perfect.
Thank you again. Okay. So we'll move on to our third speaker, and I'm just going to make sure we give him fair time. That we may run a few minutes past the hour, but we're going to make sure that Dr. Vipin Kumar is able to make his full presentation and share with us all the learnings that they've come up with on lightning strike protection for wind blades.
Sure. Thank you, Dale. Can you hear me fine?
Yep, I can, and your slide looks good, so
perfect.
Take her away.
Yeah, before I start losing people at 1 o'clock, I'll try to finish my presentation. I'll see how it goes. So good afternoon, everyone. My name is Vipin Kumar. I'm R&D staff scientist here at Computational Lab, and I'm odd one out today from the panelists who were on simulation side heavy. I'm pure experimentalist guy, so you're going to see a lot of testing data. So before we go forward, Oak Ridge National Lab is one of the largest basic energy science and material laboratory under Department of Energy. The budget is keep growing from recently, I think it's 2.6. These data are, I guess, from 1 or 2 years back. We are 6,000 strong staff, and I would say 60% of them are PhDs. And then our currency is publications, patents, and these kind of research outputs, and we are usually excel on these items. So in today's presentation, I'm going to talk about lightning strike protection, but let's give a focus on aerospace a little bit on this one today. So this is a very boring slides being used a lot, where we say like around 50% of aircraft can be made up of composites. But when we go this composites from the metal side, what do you lose? So the one thing you get, we don't get from composites, it's electrical conductivity. And when you don't have enough electrical conductivity in your composites or like in your part, what can it affect? So one of the reasons is each aircraft is usually get hit by on an average once or twice a year by lightning strike. I think it's similar data for the wind turbine blades. So any composite in the air do have a risk of getting hit by lightning strikes. On the other hand, and if you think of from the automotive sides, when you're moving more into the composites, EMI shielding, static charges, grounding, the other kind of issues are arising. But in terms of lightning strike, so what happens if you don't have a protection on your composite? If your composite is as it is and flying, what will happen to it? So let's see. You're gonna see a hole in your aircraft. I'm sure nobody want to fly in that aircraft if it's not being protected. So the current method, state of the art, is, before I go to there, what happened if a lightning hit a composite? So basically, lightning is a plasma channel. It's come with a lot of thermal energy, and this energy is stored like in this electrical pulse. When it hit a composite, it creates a joule heats because of the resistance of the composite to dissipate that electric current. And when it happened in such a short time, like microseconds, that it create shock waves in the composite, and that creates mechanical loads in your composite structures. So because of all these multiple factors, multiple physics phenomena within microseconds, you see delamination in your composite structure. You see fiber burning, resin evaporations, and delaminations. So these are general composite defects after lightning strike. So what does aircraft company do right now? So they go basics. So one of the solution is to create a Faraday cage around your structure so that the current doesn't go inside. If you have a conductive component outside, so current stays outside. So that's what the current methods look like. If you have a composite aircraft, you cover or put metal mesh around the critical areas which get hit by lightning more often. For example, nose, the wing edges. And although you want to put this metal mesh, it's not just like a metal mesh and you just stick to the composite. It takes a little bit more than that. It comes with multiple layers, and you have to create that let's say barrier between the metal and the carbon. The reason is you can get a galvanic corrosion. And even on top of that, the metal mesh usually not 100% effective. Like it does reduce the lightning damage significantly, but it still creates some kind of a scarf damage, and then you have to repair it. And as I mentioned, metals and carbon together, they don't like each other. So it's either you need to create an insulation layer between them, or you have to reduce their electrical potential to reduce the galvanic corrosion between metal and the carbon. There are other methods for lightning strike protection, especially in the nose area of the aircraft, because you don't want to have a metal mesh around your radar, because in the end you need to transfer your signals, receive signals. So the other method to have lightning strike protection is to use diverter strips, and diverter strips work as like jumping of the lightning and just go back to some grounding. But in the end, you see like there's a huge area which is not covered, and the lightning can just skip it and hit an area which is not covered. So so lightning is a big problem, but it's being handled very gracefully by the industry. And depending on the area or the location of the aircraft, you apply different thickness of the metal mesh. And these are the standards used for confirming if the lightning testing which is done to approve all these solutions are meeting the requirement to get certified by the industry. So one of that standard is SAE ARP 5414B. And the reason is I'm showing this one because I've been fortunate to get the lightning strike test done at 4 different labs in 3 different countries. And I can tell you each one of them tests it differently. So how you ground your support or ground your composite laminate, how what is the shape of your electrode will give a different response of lightning. So I think there's a research area which needs to be done on like how to synchronize all these lightning facilities to do the same kind of testing to get the same type of data out. So in my research, what I did, I tried to do with all polymeric, no metal for lightning strike protection. So I have 3 different approaches which I tried. One is I can make the whole matrix itself conductive. The second one, I put a conductive polymeric layer on top of it. And the second, I can try to enhance the electrical conductivity of the whole laminate by having interleaves, either with nano fibers or just carbon fibers. So the first approach is basically, if you see the idea one is, right now, the one I showed, you need to have multiple layers and which add weights to the aircraft, right? What if we make the whole conductive itself enough electrically conductive that it can dissipate the current? And the reason why we are trying to do it, that if I can save even 1 kg, let's say 9 kg of the total weight of the aircraft, I would be able to save a lot of fuel. So how to make a electrically conductive composite? So you have 2 options. You can either do the change in your fiber interface, try to enhance a good connection between carbon to carbon, or you can like modify the matrix, the resin system. Of course, modifying the fibers is not is more expensive and more complex than just adding fillers to a resin system, and that's what most of the people do. And even I tried the same way. Until now, the focus on modifying and making a conductive composite, it's adding nano fillers into them, carbon nanotubes, fluorine, carbon black, graphene. I went a little bit different, and I used a conjugate polymer named polyaniline, which can be made conductive. And I tried this method to see if I can make a composite electrically conductive. So this goes a little bit into chemistry, but I'll try to keep it simple. So you have a like 3 component in this resin system, where the polyaniline, which it has like an alternate single and double bond, and when you dope this polyaniline with a strong acid, let's say a sulfonic acid, you allow the charge to jump from one end to the other end and creating the electrical conductivity in your polymer chain. On the other hand, the strength comes from the thermosetting resin called DVB, which is a vinyl ester-based resin system. And again, the data says like the more you want to have conductivity, then you lose the strength. So I can improve the conductivity a lot by having more of this portion, but then I lose the mechanical properties, like it's a give and take scenario. So again, basically chemistry I talked about in this one, but let's talk what it happens, why this system become electrically conductive. So polyaniline is this black thing, and the yellow one is the resin. So when we heat and the polyaniline is get doped, it create a like it breaks down into smaller molecules and create a 3D network, and the green means electrical conductivity. But if you start heating too much, then you can see that it will start go back to its black color, which means it's de-doping. So doping is adding the proton to the chain of polyaniline, and de-doping is taking it out. And you can see with the temperature, the electrical conductivity can go from like really to 6 orders different during like, let's say within 1 or 2 minutes, depending on your heating rate. So this is how we made this electrically conductive resin system. And now if I have a resin system and I can impregnate my fibers to make a final laminate, now although my carbon fibers were electrically conductive, the resin was not. I have put the conductive resin between those carbon fibers. So I have like a fully conductive network within a composite. So what will happen? Let's see. So as I mentioned, now this is one-on-one comparison. A CF epoxy with no conductivity, a polyaniline-based resin system with higher electrical conductivity. And then you see a very good discharge, dissipation of the electrical current from the surface without seeing the damage. So this is the difference between a non-conductive composites to a conductive composites against a lightning strike. But again, industry wouldn't like to see any change in the mechanical properties. So as I was mentioned, although we are able to improve the electrical conductivity in both thickness direction and fiber direction a lot, but there's a decrease in mechanical properties a bit. So we are trying to work on how to improve that one. So that's why there's a second method I adopted. Okay, I'm not going to change the composite laminate itself, but how about I use the same coating, same resin as a coating on top of the CFRP laminate. So with that, it's a kind of same method using making my coating, but rather than impregnating the fibers, I'm just putting it on top of the composite laminate and co-curing it. So now what will happen, as I said, if there's no coating on it, you see a damage. Now this is a 0.25 millimeter thick coating on the CFRP composite laminate. So you see the fibers, the composite laminate is still safe, but the coating, yeah, did see a damage on it. So the reason is very clear that the coating act as a Faraday cage. It keeps the current on outside of the laminate and dissipate it to the ground. So you can see it took its closest line, like a distance to reach to the ground. That's why your composite laminate is safe. So I know I ran a little bit fast so that I could cover in time, but I'm happy to take any questions on if anyone has.
Thanks, Vipin. Yeah, you really don't have much time for questions, but yeah. Do you see this, as having broad applicability, not just in aircraft, but also in wind blades, for example?
Yeah, definitely. So as I said, like any composites in the air do have a issue of lightning strike, and that's where this kind of coating can help.
Yeah. And how would you compare this method to the mesh? Because I noticed you didn't look like you were doing a uncoated epoxy and then the coated epoxy, but how would you compare it to the mesh technique that's commonly used?
So mesh is by far is good, like it's a state of the art. So what I'm providing is off the shelf. Like if let's say if you have something you want to just go and paint, you don't have to like put the mesh inside. You have to put the mesh and the carbon together and co-cure them together. But in this case, this is like a paint. You just go and brush it and get it cured.
Yeah.
So this is off the shelf product, let's say.
Okay.
But in terms of the performance, I don't think it can match, or I would be at least at now be confident to replace the metal mesh than the coating itself. But it is in the right path. If I keep working on this and we can get more data out of it, I think there's a good potential to use it in all like eVTOLs or something like composite where people do like or unmanned aircraft, let's say that.
Okay. And in terms of grams per square meter, how much mass does it add?
It's a good question. So I try to match the same. So like the copper mesh or the metal mesh usually goes different from 100 to 350 GSM on the aircraft, depending on the location. The one coating I showed you was 350 GSM.
Okay. All right. Thanks.
Yeah, sure.
All right. Well, appreciate it. And that'll wrap up today's edition of Innovation Insights. Look forward to seeing you all in April. Thanks again. Thanks to all our presenters.
Thank you.
And to all of you that attended.